We have two questions in this section, both dealing with Hooke's law. So the first question says, a system obeying Hooke's law has an elastic constant K equals 4,000 newtons per meter. Find first the force when the displacement is 2 centimeters, and secondly the displacement when the force is 1,000 newtons. So as we're dealing with Hooke's law, our key formula is F is equal to minus Ks. We're told here that K, which is the spring constant, is 4,000 newtons per meter. This F here, that is the restoring force. So this is this blue here. So that's the force that wants to bring the spring back to its natural position. S here is the displacement, which, as you can tell, is in the opposite direction. So the applied force we can forget about. So we're just looking at this, the restoring force and the displacement. They're the things that matter. And again, the applied force and the spring force will always be the same magnitude, but in opposite directions. So we keep the numbers on them. They're the same size no matter what, but just in opposite directions. So in our formula, it's always this F force, which is the restoring force, the one bringing it back to its natural position. That's the one that we care about. So again, even if the applied force is compressing the spring, we're still dealing with the restoring force, the spring force, and the displacements. They're the two things that matter. And then the third thing is the spring constant. So that's the factor that makes them all equal. So focusing then on this question, we have our formula, we're told what K is, so we need to find F. So in the first part we're finding the force. The displacement is 2 centimeters, which converts to 0.02 meters. So it's reasonably straightforward. F is equal to minus Ks. We know K, we know S, so here's our answer here. Then the minus, to put that in context, the force is 80 newtons, that's the magnitude, in the opposite direction to the displacement, which is just what we looked at. So that's the significance of that minus. 80 newtons is your magnitude, and that's the important thing. You can disregard the minus at times, depending on what suits you, but it doesn't matter that much, it just gives you extra information. The second part is then the displacement when the force is 1,000 newtons. So in this question, we're told the force is 1,000 newtons. We still know the spring constant, so we're asked to find the displacement. So again, we take our basic formula, F is equal to minus Ks. That tells us that when we divide across, S is equal to minus F over K. We know F, we know K, so we substitute them in. So S is equal to minus 0.25 meters. And then again, to give that in context, the displacement is 25 centimeters. That's equal in the opposite direction to the force. So again, you can't have a negative distance, you can't have a negative displacement. The minus shows that it's in the opposite direction. So then on to question 2. It tells us when a spring is stretched 6 centimeters beyond its natural length, the restoring force is 8 newtons. Find, first off, the restoring force when the extension is 2 centimeters, and secondly, the extension when the restoring force is 15 newtons. I actually did this one an unusual way. It still worked, but it wasn't kind of the right thing, but it does show the value of this proportional relationship. So for the first part, I just looked at one in compared to the other. So here we are not told the spring constant K, but we are told the displacement is 6 centimeters with a force of 8 newtons. So those two things go together. This is our key formula. So again, my head wasn't thinking. I could have just found K using this information, which is what I do in the second part. But we do know that F is proportional to displacement. So it's not a squared relationship or a square root. It's just a directly proportional. F is proportional to S. So first, I'm told then for this first question, the restoring force when the extension is 2 centimeters. So I compared this first case with the second case, and I was able to figure out an answer, a correct answer, using just this relationship. So from the original case, the displacement, the new displacement, is 1/3 of the old displacement. So it's gone down by a factor of 3, so it's 1/3 of what it was. So the force, because they're directly proportional, that's going to change by the same factor. So when our new displacement is 1/3, our new force is also going to be 1/3. So F new is equal to 1/3 of the F original. So my new force is my previous force 8 divided by 3, because it's 1/3, so it's that many newtons. So my force at 2 centimeters is 2.6 recurring newtons. So I just looked at one in proportion to the other, and I found out the answer. However, the better way to do it, the more standard way, is you find the spring constant. You're told F, you're told S in the first case. So you were told up here again, you have 6 centimeters of displacement, gives you a force of 8 newtons. and you've got to change centimeters into meters because we got to work with our standard units. So we're told S and F, so I use that down here. So we have our 8 Newton force over our 0.06 meters. That shouldn't be centimeters, that should be meters. So that will then give me my final force of 133 and 1/3 Newton meters. So that's my spring constant. We can ignore the minus in this case. It doesn't really make any sense. It's all about direction and how one is to the other. So again, on the right hand side here, F is equal to 8 newtons and S is equal to 0.06 meters. So again, forget that C there. So then once I've found the spring constant, I can then go ahead and get my force. So F is equal to minus Ks. So F is my force, so F is my force. That's my spring constant, which I calculated. I'm told it's 2 centimeters, which is 0.02 per meter. So my force is minus 2.6 recurring newtons. So the force is 2.6 recurring newtons in the opposite direction. And then I squashed in the second part here. So we're asked, I haven't done this one before, so let's take a look again. We're asked the extension, which is our S, when the restoring force is 15 newtons. So here I know my K, my spring constant, from this work here. I don't know my displacement. I'm told my force is 15 newtons. So this is my standard formula. F is equal to minus Ks. So when I divide across, S is equal to F over K. And again, I just left out the minus. It's not too significant in this case. I just want the size of the displacement, the magnitude, the direction. I know it's opposite, but I don't have to keep saying that. So S is equal to F over K, 15 newtons over 133 and a third newtons per meter. So my displacement is 11.25 centimeters, 0.1125 meters, but centimeters is a better unit. So there are a couple of quick questions dealing with Hooke's law. So make sure you can do those and similar, and we'll be building on these as we move forward. But this again, F is equal to minus Ks is our typical formula, and the cousin of this is F is equal to MA, which will be linking the two together later on.